Welcome to part 2 of the Watershed Factors lecture. And at the end of the first lecture, I revealed to you the list of watershed factors and gave you a brief description about those. Now we're going to go a little more in depth about how those factors affect runoff in the watersheds, how they govern runoff in the watersheds. All right, so just to recap, won't spend much time on it, but our watershed factors are size, topography, shape, orientation, geology, climate, soil, and land use. These are all very interconnected with a lot of feedbacks between one another. I used an example before that soils are a function of the geology as parent material, the climate, which helps determine how those parent materials break down and are converted to soil, the vegetation, which also affects that, and topography. So these are all very interconnected, and then land use and soils are the two that as humans we have the most impact on, and in many ways, especially soils, are some of the most important. Soils is probably the most important watershed factor in some ways, if you made me pick one. All right, so the size of the watershed, that first factor, this determines the potential amount of runoff that's captured by the watershed, all else being equal. So here I've got a figure that shows the Mississippi River watershed, which covers most of the central part of the U.S. all the way up into the southern part of a couple of Canadian provinces there. And so it's a big watershed, so it's going to capture more water than a smaller watershed would. And also it's going to have more varied soils and land use and vegetation and all those other things, all those other factors. They're just going to be more varied across a watershed this big. Also travel times. If you're a raindrop that falls way up here at the mouth of the Missouri River near Yellowstone National Park, it's going to take a little while for you to make it across that landscape into the Missouri and eventually get all the way down to the Gulf of Mexico. So the residence time in the watershed would be larger in a larger watershed. Topography. So here I'm showing you a photo from Rocky Mountain National Park in Colorado. You can see we've got a stream here in the foreground and mountains in the background. If you think back to what you know about topographic maps, the contour lines in the topographic map delineate points or lines of equal elevation. And if you recall back to whatever geography or geology lab that you had where you learned to read topographic maps, you may remember that water flows perpendicular to contours. It means that it's perpendicular to contours is the steepest pathway across the landscape. So if you're a water drop that falls up here on this mountain that's on the left side of the picture in the foreground, that's pretty steep. And gravity is going to be a major push. Gravity is going to have a lot of influence on sort of pushing you down that slope faster than if you're a water droplet, a raindrop that falls out here on the meadow, this relatively flat area. Gravity is less important. You're going to fall, and gravity is not necessarily going to push you left, right, backwards, or forwards on this flat meadow. You're probably going to be more likely to just sit there and infiltrate or evaporate. Versus on that slope, those things can happen. There's probably some soil. You can see some of this is bare bedrock, but as you get lower down the slope, there are some soils there. There are trees and vegetation. But because gravity is trying to push you down, it actually gives you sort of some momentum and an inertia that may prevent as much water from infiltrating as if you were on an otherwise flat slope. And also, steeper slopes with water overland flow on them can erode very heavily. So erosion can be a lot greater factor in a watershed like this. Okay, the shape. So we talked about shape before, but it affects the average distance between the watershed boundary and outlet. So in watershed A here, we have a watershed. You can see there's really no point in this watershed that's all that far from a stream channel, the black lines being the stream channel. So even if maybe this is the furthest point in a watershed from any stream channel, just the travel time, regardless of if it's overland flow or interflow or whatever, it's just going to be less to get to the channel. And once you get in the channel and you start stream flow, you can move pretty rapidly towards the mouth of the watershed. Whereas in this bigger watershed B over here, it's just your residence time is going to be bigger here because there's more land, there's sort of relative to the area of the stream channel, there's more area of just landscape out there for interflow, overland flow, interception processes that we talked about in lecture 1 to take effect. So orientation or aspect. So let's just assume, I know visually it's not quite equal, but let's just assume for a second that these two watersheds are equal in every way except for their orientation. So B and A both have the same area, the same geology, the same climate, same topography. Everything's the same except A is more north-south oriented and B is more east-west oriented. Okay, that has a couple of important outcomes in terms of how water translates to runoff. So let's imagine where my laser pointer is over here, we've got a thunderstorm that's moving west to east or left to right across this landscape. So I'm trying to keep the pointer moving at a steady rate. How long does it spend over watershed A versus over watershed B, right? So obviously the time that same rainstorm rains on B is a lot longer than A because it's moving more perpendicular to the orientation of A, so it just doesn't dump as much water. If that rainstorm's dumping an inch per hour of water and it only takes 1 hour to go this distance, but this distance is 3 hours, it's going to dump 3 times the amount of water, right? So the same rainstorm then, the same exact thunderstorm, as it passes over this might cause just a little flood or no flood, but here it could cause a great big flood because it just rained on it longer. But also, most days in a watershed, most days in most watersheds, it's not raining. In a watershed like this, that's north-south oriented, we probably have our steeper slopes out here on the left and the right, or the east and the west. Because of the orientation, we know there's going to be a stream valley down the middle. That'll be the lowest portion of the landscape, so hence the highest portion has to be out here along the watershed boundary. Because the morning sun and the afternoon sun are somewhat different in the time of day, if no other reason, the time of day and the temperature, we might affect some of the slopes here that face east on this side. They face, when the sun's over here shining on these eastern slopes, or these western slopes, the eastern ones are in the shadow. But then in the afternoon, when the sun's over here to the west, it's directly, and the day is warmer at that point, it's directly shining on these east-facing slopes. These slopes may end up being a little drier because they're getting direct sunlight at a warmer time of day, which is going to drive more evaporation. And if you look carefully in a watershed, especially watersheds that are in places where rain is a little less abundant than, say, Missouri, like out west, you usually see a whole different set of vegetation on western slopes than eastern slopes, and the same with north and south. Southern slopes, like in B here, southern slopes are going to tend to be in the shadow most of the day because in the northern hemisphere the sun's always going to be to their south even in the summer, and the slopes on the north side of the basin, which face to the south, will get direct sunlight through almost all day. So they'll be drier. So in some watersheds, and this is true, I did a lot of work earlier in my career in Minnesota, and even Minnesota is a humid area like Missouri, but in the watersheds up there, a lot of those slopes that face south on the north sides of watersheds tended to be drier, more xeric conditions. So traditionally, historically, these slopes were prairie, and the south slopes were a little wetter because they were more in the shade during the day and they had more trees on them. So this orientation can affect the distribution of vegetation in the watershed too, not just how long it gets rained on according to the orientation of the storm. So lots of ways that orientation can matter, and I'll just say that aspect and orientation are synonyms. I put both here. I usually use the word orientation, but you'll see sometimes in the literature called aspect. Exact same thing. All right, geology. So geology does several things to our watershed. First, it defines the boundaries. I guess you could argue technically it's topography that forms the boundaries, but geology is sort of a control on topography to some degree. The type of bedrock you have, the distribution of that bedrock, how easy that bedrock is to weather. So if you've got really competent, hard to erode limestone in one part of a watershed, and you've got a soft, poorly cemented sandstone in another part of the watershed, that sandstone is going to erode easily, so that will become the low point in the watershed where the stream valleys are, and that resistant, erosion resistant limestone will become the high points. So it sort of sets the conditions where the topography will be determined. But then that also, the types of bedrock and how resistant they are, more resistant bedrock like limestone that are generally harder to erode, you're usually going to get steeper slopes there. Softer to erode materials will be eroded sort of flat. They'll just be flattened by erosional processes over time, so they aren't going to have as much gradient. You're also going to get different soils. If you've got a limestone like we have here, most of the Ozarks, southern Missouri, is carbonate or limestone and dolostone bedrocks. Dolostones and limestones tend to dissolve when they weather. They don't break down into smaller pieces. They just dissolve away. So you don't get much soil, and the only impurity in most of these carbonate rocks like we have in the Ozarks is clay. That's why you have clayey soils here. We have thin clay soils. They're thin because the percent of the impurity in the bedrock that doesn't dissolve is small. So after most of the bedrock dissolves, there's only a tiny fraction left over to form a soil, and that impurity tends to be clay, and so we get clayey soils that have poor permeability, poor infiltration, and tend to mean that our landscapes are really flashy. If we get even an inch of rain in a couple hours, we're going to have some runoff on the surface, versus other parts of the country, other parts of Missouri, like northern Missouri, where they have deeper glacial soils. An inch of rain an hour probably wouldn't even get close to saturating a lot of their soils that they have up there, because they have so much more porosity, so much more permeability. And then climate is another factor, a watershed factor, and I've got it on this graph because climate often plays into some of these other processes we're talking about. Like if you have a really wet climate, your weathering rates will be much higher. I mean, it makes sense. Weathering is defined as the breakdown of rock, either chemically or physically. That's driven by water for the most part. You have to apply water to erode bedrock, to weather bedrock. Weather is the breaking it down. Technically speaking, in geology, erosion is transporting the broken down particles. Weathering is the breaking down of the particles, and erosion is the transportation of those particles. In day-to-day conversation, even geologists are a little loosey-goosey with that. We'll use erosion when we should be saying weathering. But my point is here that in a wetter climate, weathering rates will be faster. In a drier climate, weathering rates will be slower. Erosion may be just the opposite. In a wetter climate with more vegetation, the vegetation holds things together. So you weather the bedrock, but the roots are holding it in place, and it can be actually harder to erode than if you're like out in the western U.S. where you don't have much vegetation at all. And when it does rain, it can be these monsoon rains that are really hard, and they can cause lots of weathering, and then the erosion can just go crazy because there's no vegetation, because you're in basically a desert. There's no vegetation to hold anything in place, and so all that water just carries away all the weathered materials. So climate can be important in that regard. Climate also dictates some of the relationship of, say, a surface stream to a water table, and the previous lecture on watershed factors in an earlier lecture this semester in an earlier module, talked about how in places like Missouri, the water table is sort of expressed at the surface as the surface of the water in a stream channel. That's called an effluent stream with an E. That means that the water table here is contributing water to the stream. And we talked about earlier that this type of stream The reason we have base flow, if you go out to a stream in Missouri or many parts of the world and you look, it's flowing, but it hasn't rained in a day or 2 days or 3 days or 2 weeks, but it's still flowing. It's because that base flow is being driven by contributions by effluent from the water table and some inner flow through the soil, that even though it might not have rained for days, that water that's moving laterally in the soil through inner flow, which we talked about in the previous lecture, is still moving through the soil and contributing too. If you go to a more arid climate, like in the southwestern United States or any part of the world that's a desert, streams have a different relationship with the water table, and we're going to do a whole module later in the semester on groundwater, and we'll go deeper into this concept. But here you can see that the stream is actually the high point. It's still an expression of the water table, but in this case, let me change to pen here. In this case, over here in an effluent stream, water's moving from the aquifer into the stream to feed base flow. In this influent situation, most of this water is coming from snowmelt upstream, like in the Rocky Mountains or the Sierra Nevada. So you hear about this a lot. You probably read about it when we talked in our discussions and when you were doing your reading for the discussion on California wildfires. The water that they have in their reservoirs and in their streams is snowmelt for the most part, because they can go months and months, even whole years, without any significant rain. So it's snowmelt that when that snow melts, that flows down streams, and then those streams are recharging the aquifer, so water's moving from the stream to recharge the water table. So our net flow is that way. And if it does rain, that precipitation comes down, hits the land surface, all those interception processes and stuff still apply, but that water will either move as inner flow and maybe emerge out onto a stream bank, or it'll percolate down to the water table and recharge in that direction. But it's not going to get to a stream if it does that. It's going to go this way, away from the stream, because that's the way water is moving. Versus here, if water infiltrates and percolates, it's going to hit the water table, and then it's going to move towards the stream and eventually contribute to the stream as base flow. All right, soil. We've already talked about how important soil is. Soil is like a great big sponge out there in the landscape, and I love this analogy because you could literally go to your dorm room tonight or home to your apartment or your house, get a sponge out, you probably have one, put it under the faucet in your sink. Just set it on the bottom of the sink under your faucet. Now, I'm assuming that sponge is dry or at least wrung out pretty well, so it's got a lot of available pore space and porosity. And sponges by definition are very permeable. Pore space is how much space there is in there to hold water inside the sponge. Permeability or infiltration rate is how fast the water can move into those pore spaces. Now turn the water on in your sink just slowly. I mean, if you turn it on really fast, some of it will soak into the sponge, but it'll be coming so fast it's like a really heavy rainstorm where the water's raining faster than it can infiltrate in the soil. So it could technically get into the soil, there's pore space available, but it's raining too fast for all of it to get in, and some of it has to run off. So you could do it both ways, but what I would do is try it both, is wring the sponge out really good, turn the water faucet on just a light little bit, just a tiny sort of, more than a drip, but just a steady flow. What you'll see is all of that water gets captured into the sponge for a while. And until that sponge fully saturates, really very little water will flow out of it and go down the drain. The sponge actually stores a lot of that water. Now, after the sponge becomes fully saturated, at that point, almost all the water has to run directly off. There's no more room to store water in the sponge, so any new water, additional water that falls on the sponge from your faucet is just going to run off the top of the sponge, go down into the sink and down the drain. Now, if you turn the water off and you watch the sponge for a few minutes, you'll see that water slowly draining out of the bottom of the sponge and going down the drain. That's what soils do. It rains, even if it rains pretty hard, a lot of that rain gets captured by the soil, and then the soil will very slowly release that water through interflow and other processes like that back into the stream, or allow it to pass through all the way through the soil and percolate down to the groundwater. So sponges are just a perfect analogy just about for soils. And then you can run the experiment the other way. Like I said, wring the sponge out all the way and just go from 0 to 100 on that faucet. Just turn it on as hard as you can go, and you'll see that a lot of the water just bounces off, runs off faster than the sponge can actually infiltrate. Eventually enough water will get in there to saturate it. You'll get to the same condition. But even initially when the sponge has a lot of ability to absorb water, it's just running too fast. And if you want to test the influence of slope on this, take your sponge and prop it up with something so that it's got an angle to it, and then do the exact same experiment at the exact same rate, like turn the water on really slow. You'll see the infiltration capacity will decrease because some of the water will just run, gravity's going to push some of the water right down the face of the sponge before it can infiltrate in. What this picture here is showing is an area of soil where, before they dug this all out, they took a square of ground here, a rectangle of ground, and they poured blue dye in it. And then after the dye, they gave the dye a little while to infiltrate through, and then they dug it out. And what you can see is a cross-section. They cross-section this part here, so you can sort of see a vertical cross-section, and then this part a horizontal cross-section. And here you can still see the surface, so they poured the dye over this whole area right here. And you see the dye shows you where the water infiltrated. And the water goes pretty deep, it'll follow, but soils are not homogeneous. So you can see, like in this part of the soil, all the water, as shown by the blue dye, went pretty much everywhere. There's a few gaps here and there, but over here, very little of the water actually infiltrated through this part of the soil. It could be different reasons. It could be that the root density is greater here, and roots are sort of a pathway through the soil that's path of least resistance. The roots already sort of drilled a hole through the soil, so it's an easy place for water to just follow down the side of the roots, especially if it's a dead root where the plant has died and the root has mostly rotted away. What's left is called a macropore, so it's sort of like a mini straw right through the soil, so that can be sort of a super highway for infiltration. Versus over here, maybe there's fewer roots, although it looks like there were plants there. It also could be that this part of the soil just had a slightly higher concentration of clay than this, or this part had a slightly higher concentration of sand and silt, which are more permeable. So that higher concentration of sand or silt made it easier for water to move through this, but over here, because there's a little extra clay right there, it was just harder, so the water took the path of least resistance. And a major factor, once again, bringing climate into this, a major factor in soil formation is climate. Climate controls those weathering rates that we were talking about, and those weathering rates are part of when you weather the parent material, the geology, in combination with soils and vegetation, you create soils. The other thing here that I do want to point out is soils are different, and different soils have different pHs, different chemicals in them, and I'm not talking about pollutants necessarily here, just different ions and anions, and as water moves through the soil, it can pick those things up. And so soils also play a role in water chemistry. Land use versus hydrograph, I'm not going to dwell on this too much. I'm going to do a separate lecture just on this graph, more or less. But what I want to make the point here, until I can go deeper in this, is imagine you have one watershed, and with the wave of a magic wand, you can make the whole watershed urban. Well, this is a hydrograph, so it's the amount of stream flow graphed versus time. What you see here, let's just imagine that we put a great big rainstorm, like in a couple of minutes we dump a huge rainstorm on this watershed, and then we turn the rain off. In an urban watershed where we have lots of impervious surface and not a lot of soil, we'll get a really flashy hydrograph. So the flood gets really big, so really deep, think deep here. We get a deep flood, and it occurs quickly. The time from rainfall to flood peak is short, and then it rapidly decreases afterwards. So this can be a catastrophic flash flood. In a forest, and we've got sort of a continuum here, urban, agriculture. Agriculture, we have some disturbance, but obviously in agriculture you have a lot of soil available, or not a lot of impervious soil. And then sort of ag/forest, and then forest. And in Missouri, we might put forest on this graph, but it could also be prairie. Prairies are even better than forests in some way at absorbing water. But because the forest has all those trees, all that vegetation that's able to cause interception and make it harder for water to get to the soil and more time for evapotranspiration to occur, the flood peak in the forest is smaller. We don't get as big a flood, and the duration from when it rained to when that flood peaks is a lot longer. I mean, it's many times longer than it was in the urban setting, and then it slowly comes back down. So land use has an important role in determining how much and how fast water gets into a stream. So just to close here where we started, we have all these watershed factors, and they all work together. So as we went through this, we talked about each factor individually, but if you noticed, every time we talked about one factor, we were describing it in the context of how it interacted with other factors. And by no means did I go through all the possible interactions. So the take-home message is these are complicated sets of interactions, but it's this, every watershed has a unique set of these characteristics, these watershed factors, and so each watershed is going to have a different ratio of how much rainfall actually ever becomes surface runoff. Some watersheds may yield most of the precipitation as runoff because they don't have much vegetation, they have steep slopes, poor soils, things like that, so there's not much to slow the water down. It just rains and it gets straight in the stream. Other watersheds, like a flatter prairie, pre-settlement prairie in Kansas or Iowa or Minnesota or something, it would be really hard to even get stream flow in some of those systems historically, because the prairies just had such deep root systems, deep soils. The soils were so permeable, they could hold so much water. And then they could transpire so much, and the roots held everything together. And so you got a whole different watershed response there. All right, that's where we'll end this one. Thank you.